Okay, so last time we ended with our discussion of linear fractional transformations. So most importantly, one of the last things that we said was that linear fractional transformation maps this projective line that I've written here as R union this point that I'm calling infinity onto itself. Okay, and so to see that, of course, we had previously seen that there was a nice way that these linear fractional transformations actually allowed us to divide by zero, basically, right? These linear fractional transformations allow us to divide by zero, and so there was a way to assign because if we didn't come up with this characterization in the projections that we previously discussed, there were points that didn't match up, right? So zero didn't map to anything, and and nothing mapped to it going in reverse or mapped from it going in reverse in the other way. So basically, in the simplest example of where this is a problem, so like inversion, for instance, right? We actually saw this in the picture, that not every point mapped to all of the other points. So this was, for instance, right, in this picture, I had to dig through it. So in this picture, right, this point on L1 is not getting projected to anything, just looking at the picture on L2, it seems. What it's actually getting projected to, of course, is the point at infinity, right? Similarly, what maps to this point on L2 from L1? Well, no point on L1 in this sense, but the point at infinity maps to this this zero on L2. And so this is one of the things we saw previously. So that's what led us to come up with this description. So anyway, so having this, so for a general linear fractional transformation, not just inversion 1 over x now, if x is minus d over c here, right, then x gets sent to infinity, right? And so in that same projection image I just showed you, the thing playing the role of 0 is minus d over c here. This is our 0 for a general linear fractional transformation. And so anyway, using this allows us to extend the reals to include infinity in this way, where this is the point that gets sent to infinity. Likewise, infinity gets sent to, infinity in this case would get sent to a over c. So x equals infinity gets sent to a over c, so maybe I should include that here. So if x is equal to infinity, this gets sent to a over c. All right, because otherwise, a over c is something that doesn't get mapped to here. Okay, so no real value of x gives this f of x a value of a over c, but x equals infinity does, or at least if we define it to be that way, then it does. Okay, and so using this description of fractional linear transformations, this function maps a projective line, which I'm calling R union infinity with itself. Now, I keep calling this thing the projective line. So what do I actually mean by that? So we can finally stop the hand waving, and we can finally define RP1, the real projective line. So we've kind of been dancing around this the whole time, right? So we were kind of speaking of it generally as an abstract thing that we thought of as, being a simpler object than, say, the real projective plane. But what is the real projective line? So RP1 is the set R union this point that I'm calling infinity, which is a point not in R. That's what's important here. Okay, together with all the linear fractional transformations. So all the linear fractional maps mapping R union, oh, why did I write that as a literal U? R union this point at infinity to itself. Okay. I mean, even better, we can say onto itself, right? These are actually correspondences. Okay. Note, RP1 defined in this way. Has all the properties we expect of what a real projective line should be. Of a projective line. Okay. Okay. All right. So, why? Why is this the case? Or why can you see this from what we've said here? Well, the answer is, note that RP1 is not as rigid. It's not as rigid as R. What do I mean by that? Well, for instance, once you've selected where 0 is, so once you've selected where 0 lies, and where, say, 1 lies, then your line R is determined. Okay. What do I mean your line R is determined? That means every point on R is uniquely determined. I know exactly where it is once I know where 0 and 1 is. Okay. Using my familiar multiplication and addition here. Okay. And so, but this isn't true for RP1. Okay. Because there's a projection sending 0 to 0, 1 to 1, and 2 to 3. Well, what does that mean? What this is saying is that since RP1 is taken to be this set R union infinity, or some point we're calling infinity that's not on R, together with these linear fractional maps that map this set onto itself, these linear fractional maps are they are key invariants of this space RP1. They are the things that we'll see help really like tie together the geometry of RP1. And so these things are playing the role of the isometries in the case of like R2, for instance. Okay. And so what did the isometries in R2 fix? Well, they fixed length. Okay. So these linear fractional functions, they don't fix length, right? Clearly. So for instance, this specific projection, sending 0 to 0, 1 to 1, and 2 to 3, doesn't fix length because it doesn't respect the length between the image points. So for instance, the length between these two is still 1, which is what it was when you started out, but now you've stretched the length between these two to be 2 instead of 1. Right, and so it's not an isometry, right? You know that projections are not Euclidean isometries, typically. But we'll see here in just a second that it fixes some other thing. It doesn't fix the length, but we're in projective geometry, so that's totally fine because we're in projective geometry. Length doesn't even exist to us, right? And when I say length doesn't exist, of course, what I mean is that if we're going back to our original description, we're doing straight edge constructions alone, right? So we have no way of marking off, say, equidistant points. We have no way of drawing an equilateral triangle with just a straight edge. So length has no meaning for us, no importance to us in the projective setting. Okay, so this is actually fine. So there are projections that map in this way, meaning that there's two different examples of an RP1 where just because I've specified where 0, 1, and 2 are, I could change them up a little bit with a single projection. Of course, this isn't the only choice. I could have made many more choices here. In fact, I could have made any 3 choices, as we'll see. Okay, so I have a couple more things to say about RP1, but I think I will leave it until the end, until after we're done with what I was saying before. You may have seen this, depending on your background of what you've seen before. You may have seen this in some form. I'm going to go back to our discussion of this. The first time I mentioned RP1 or a projective line, I modeled it using a circle. Okay, that's an important example, and that's actually typically how I would think of it if I were thinking of this off the top of my head. And I'll get into that a little bit later, because if you've seen any topology, or if you have seen, depending on what setting, like I said, you've come across this kind of thing before, you may have seen some different terminology associated with this, and I wanted to at least mention that for a couple minutes. Okay, and so RP1 is this line. Now, or is this set. It's R union a point not on R that we're calling infinity. Okay, well, you know what? Maybe I'll go ahead and do this one. So, recall our first model of a projective line. So what was our first model of a projective line? We had a line, we had the origin, say, here at the line, and then we had a circle that was tangent to the line there. Okay. Okay. Here's another way of thinking about RP1. So another way of thinking about RP1, think about the plane, as usual, and think about, it doesn't have to be a unit circle sitting here, but let's think about a circle centered on the positive y-axis that is tangent to the x-axis like this. Okay. And so what I want to do is I'm going to define the point P to be my north pole of this circle. Okay, so P is my north pole. And what I'm going to do is think about light shining toward P in various directions, and I'm going to just draw the light rays. Okay, so I'm just going to draw the lines through P. So there's already one line through P, the y-axis itself. Okay, but I'm gonna ignore that for a second. So that's not gonna count. Okay, so we don't count we don't count that one. All right, but every other point, okay, on this circle is going to be associated to some point on x, or on the x-axis. Okay, what do I mean by that? So, for instance, here's another point, say P1, and the point on the x-axis that P1 is associated to by this mapping is this one. So this is P sub 1 prime, we'll call it. Okay. Similarly, here's P sub 2. And what is the point? P sub 2 prime. Okay. What about points over here? Right? Okay, so here's point. It's associated here with, if this is called P sub 3, we'll call this P sub 3 prime. And in this way, in fact, even this point here, right, is just exactly equal to a point that's already on the x-axis. Every single point on this circle is, or corresponds to some point on the x-axis, except one, right? There's a point on this circle that doesn't correspond to the x-axis, or any point on the x-axis. Note, the point P corresponds to no point on the x-axis using this map, or using this transformation, we'll say. Why? Well, all of these lines are defined to be the line from P to some point on this circle, right? We actually saw this in reverse when we first talked about this projective line, right? So why did this behave like a projective line? Because every point on this thing had a line associated to it, right? Oh, well, okay. So every point on this circle has a line associated to it, and we know that that's how projective lines behave, right? So there we go, right? So each point is actually a hidden line, right? In some sense, this is how we defined our models, or our real models for projective. Well, not just the real ones, actually. It's how we defined all of our models for projective spaces of various types. So anyway, this point P corresponds to no point on the x-axis using this transformation, because if we tried to draw the line from P to P, what line would that be? Well, it would be this tangent line. And we draw the tangent line passing through P, then what do you notice? Well, this line's parallel to the x-axis, so it doesn't intersect it anywhere, so it doesn't intersect any point on the x-axis. All right, but P maps to the point infinity. Right? It maps to the point at infinity. And so if we set up this mapping to take us to a point on the x-axis, right? Of course, as these points get closer and closer to this north pole, as they get closer and closer to P, these lines are getting further and further out along the x-axis. Okay, but of course, as those points limit to P, the line is actually parallel to the x-axis, so they meet only at infinity. So this point P gets sent to infinity. This is called stereographic projection. You can do this in more dimensions. In fact, it's really nice to see in 2 dimensions. So this is called stereographic projection, and it's tied to this description we have of RP1. Okay, so the thing that I'll leave until a little bit later is there's also something called a one-point compactification that ties in with what's going on here. Okay, and I'll talk about that later. Now, the next thing I want to talk about is the reason why I have a PhD. This is the cross ratio. Which is, I can't possibly overstate its importance to us, or really to geometry. This is an extremely, extremely important thing. In fact, I'll read this quote here just because it's funny. So this is from another similar sort of geometry book that tries to build up from complex and straight edge constructions. It's called Geometry, Euclid, and Beyond. It's a good book, so if you're interested in another treatment of this, it's the same kind of material, basically. It's by Hartshorne. Anyway, the quote is, "You might say it was a triumph of algebra to invent this quantity that turns out to be so valuable and could not be imagined geometrically. Or if you are a geometer at heart, you may say it is an invention of the devil and hate it all of your life." So the cross ratio, what is it? Well, first, we know that the projections, remember, projections are associated with linear fractional transformations. There's a correspondence between those. So whenever you see the word projection, you can think of linear fractional maps. Okay, even though, projections are these fundamental transformations of projective geometry. But of course, they're associated with these linear fractional maps. So we know that projections distort the image in some way, i.e., length is certainly not preserved. Right? Okay, so we know that length is certainly not preserved. So you start out with, say, equal lines. After a projection, what you get is something that is decidedly not equal. Well, what's our example of this? Well, our example was this tile, right? This nice tile picture that we keep referring to. There's this tile view of the plane. Now, when you look at this, right, your mind recognizes that these tiles are of equal size, right? Even though, of course, if we actually were to break out a ruler and measure these, they're clearly not of equal size in that sense, but they look like they're of equal size, right? In fact, we could imagine that there's a projection that takes a nice square grid of square tiles that are actually of equal size, right, in Euclidean sense, and projects them onto this picture, right? We talked about that. Okay. And so you look at this, and it looks like these are equal. They're not equal, but it looks like they are. So the fact that I can say that it looks like they are, means that something about this picture is being preserved. Okay? It's not length. Length is not being preserved here, that's clear, right? Because they're not actually equal size. If length were being preserved, then these would literally be equal size. If I broke out the ruler, I could measure each side length and you'd get the same thing. So that's clearly not the case. So then you might say ratios of sides are preserved, right? But you can actually measure that as well, even using this picture, and it's just clearly not the case. Okay, so ratios are also not preserved. So length is certainly not preserved. Well, ratios of lengths are not preserved. Okay. But it turns out that ratios of ratios are preserved. Hold on, I have to remove my cat. Oh, say hello. There's the cat. But yeah, anyway, so ratios of ratios are preserved. So this ratio of ratios is called the cross ratio. All right, and so what is it? So this ratio of ratios is the cross ratio. All right, so what is it? So here's the definition. The cross ratio. Okay, cat keeps coming back. Stop it. So the cross ratio is a quantity associated to 4 points on a line. Okay, so it's associated to 4 points on a line. We'll call them PQRS. So if the 4 points, they're on a line, so they only need a single, number or coordinate to describe them. So if the 4 points are P, Q, R, and S in coordinates, okay, then their cross ratio is defined, oh, I'm off the page, is defined to be the following quantity that I'm going to write like this. So we're going to use this notation PQ semicolon RS framed by square brackets. Okay. So what this is, to see that it's a ratio of ratios, it is R minus P over S minus P over R minus Q over S minus Q. Okay, this is not the form we usually write it in. We simplify this a little bit. So how do we simplify this? We simplify this as R minus P, S minus Q. So bring this to the top. So R minus P, S minus Q divided by R minus Q, S minus P. So this is the way we write the cross ratio typically. Okay. All right. So the way that I like to remember this, from this notation here, the way you remember the order and how this goes. So basically you look at these things and we'll go just from left to right, top to bottom. So this first term is R minus P, so that's first and third. Now you might say, well, what order do I go in? Here I have R minus P. Could I choose P minus R? You could, but whatever order you pick, you have to stick to that order through the whole thing. So you can't do R minus P in the first and then do S minus Q, then do Q minus S in the second, unless you also have a flip happening in the denominator. So don't do that. Just pick one and stick with it. So pick some ordering and stick with it. So in this case, you would have R minus P, so that's first and third matched up. S minus Q, so that's second and fourth matched up. Then R minus Q, that's inner, and S minus P, that's outer. Okay, so the numerator is first and third, second and fourth. And those two things are multiplied. And the denominator is inner, R and Q, and outer, S and P. Okay, this is the way to remember it. Okay. All right. So, you look at this thing and you say, wait, what is going on here? What is important about this? So the key thing of importance here is that, well, I would be tempted to say the key fact here, but the cross ratio has so many nice things about it that I don't really want to pigeonhole myself into that issue. So I'm just going to say big fact, theorem, whatever. We're going to prove it, so it's a theorem. The cross ratio is preserved by projections. Okay. So the cross ratio is preserved by projections. Now, what do I mean by that? Going back to our discussion before, right? We knew that projections don't preserve length. Okay. We know that they don't preserve ratio of length. And if you don't believe that, just try it. Okay. Just take equally distant points and project them in whatever way you want to, okay, and you can check the ratio, right, and the ratio of the lengths involved and whether or not they're preserved, and they're just not typically. Okay, but we're claiming that projections do preserve the cross ratio. Okay, and so this somehow ties in with what we were saying earlier when we were looking at that tiled floor, that we look at that perspective view of a tiled floor, and something in our brains tells us that these are equally spaced tiles, even though there's absolutely on the surface, there's no info in that picture that should tell us that that's the case. Well, this hidden info I'm claiming is the cross ratio in some way. So it's the fact that the cross ratio is being preserved that allows this perspective view to look, accurate or realistic. Okay, so I only need to check the three things that make up every projection, right? So I only need to check the simple projections. So the simple projections are the one sending x to x plus L, the dilations, and the inversions, right? So I only need to check these projections because every projection is a combination of these, right? So I have three cases to check. Okay, so let's check the first case. So projection 1 sends x to x plus L. So bringing back my cross ratio for a second. If I do that, what happens? All right, so the cross ratio, PQ RS, gets sent to P plus L, Q plus L, R plus L, S plus L. But what is this? Well, this is, if I just write this out, remember it's first and third, so it's R plus L minus P plus L times S plus L minus Q plus L over R plus L minus Q plus L times S plus L minus P plus L. So what happens here? The L's cancel in every single piece of this cross ratio by subtraction, and what are we left with? We're just left with the normal cross ratio. And so the type of projection that could be viewed as this translation, right? So this is projecting from a point at infinity. This, this sends the cross ratio of 4 points on a line to itself, right? Okay. So remember, the cross ratio is defined for 4 collinear points. The 4 points have to be on a line, or the cross ratio doesn't make sense. Okay, let's check the second case. All right, second case is dilations, but dilations behave the same way. All right, so PQRS, that cross ratio gets sent to KP, KQ, KR, and KS. Okay. All right. But this is equal to the same. Well, maybe I'll go ahead and write it out. It's just good to see this stuff sometimes. So this would be KR minus KP times KS minus KQ, right, over KR minus KQ times KS minus KP. Right, but again, each term I can factor a k out and cancel it with the k from below, and I don't have to worry about k being 0 here. I don't care about those dilations. So so k is non-zero here, right? And so again, this is just equal to the cross ratio. Through division, I just cancel those things. Okay. All right. And then lastly, this is the one that takes maybe a little bit more work. Maybe it's not as obvious how this works out algebraically. Let's go ahead and do it. So case 3, I am inverting. So my PQRS cross ratio gets sent to the cross ratio 1 over P, 1 over Q, 1 over R, 1 over S. Okay, and so what I get here, what is this? This is the cross ratio that is 1 over R minus 1 over P times 1 over S minus 1 over Q divided by 1 over R minus 1 over Q and 1 over S minus 1 over P. Okay. So there's our cross ratio. Now let's clear denominators here. So if I clear denominators in this term, so I multiply by RP, what do I get? I get P minus R, right, on top. So I get P minus R over RP times, if I clear denominators in this term, I would get Q minus S over SQ, and that is divided by, clearing denominators here, I would get Q minus R over RQ times here I would get P minus S over SP. Okay. But then what do I get here? In the denominators here I have RPSQ, and here I have this should be SP, sorry, not SQ. Alright, that would be bad. Okay, so in the top I have RPSQ, and here I have RPSQ, right? So I have the same things there. These cancel. So what I'm left with is cross ratio P minus R Q minus S divided by Q minus R P minus S. That's equal to the cross ratio. Let's just see that. I can flip every single sign here because there's 4 of these, so those things cancel. And so I have R minus P, S minus Q. I have to flip every single one. R minus Q, S minus P. Right. And so this is just the cross ratio, PQRS. Okay. All right. Thus, maybe I should say one more thing here. Thus, since any projection is a combination of these three, is some combo of these three, the cross ratio is preserved by projections. Okay. Now, we're going to see a long list of facts about the cross ratio that we'll start with today, but we won't finish until next time, that fully explain why the cross ratio is so important. So you might look at these properties. Let me just go back through them real quick. So our cross ratio is preserved by operations sending x to x plus l. So these translation things, that's one type of projection. So it's preserved by that type of projection. It's preserved by dilation type of projection, and it's preserved by inversions. Now, because of how simple the algebra was in showing this, you might not on the surface be that impressed by the fact you have this quantity that's preserved by these three things. So then my challenge to you is, if you think that maybe this isn't that special of a thing, try to come up with some other quantity defined on 4 points that basically come up with some other quantity defined on 4 points that has the same properties. Okay. So don't try too hard on this. Don't try too hard. But it turns out that basically, in a very rigorous sense that I'll 100% be precise about, the cross ratio is more or less the only such thing. Okay, it is the only such, we'll say, invariant of 4 points in this way. Now, why do I keep insisting on 4 points? Because it turns out that 3 points is not enough. Okay, 3 points is not enough. So I hinted at this when I mentioned this fact before we talked about the cross ratio, where when we're dealing with real projective line, one way to see that it was not as rigid as R was that in R, once you had specified where 0 and 1 were, then that specifies exactly where all the points are on R. Okay, but that's not the case on a projective line, because there are projections that take, say, the 3 points 0, 1, and 2. There's a projection that takes it to 0 to 0, 1 to 1, and 2 to 3, for instance. Okay, so there are projections that do that. In fact, you can send 3 points to any other 3 points you want. Right? So this is a key thing. Okay, this is a key thing. Compare and contrast this with the theorems that we proved about isometries of the plane, right? The 3-point determination theorem, for instance. Okay, and you'll see how different this is. Okay, so that's why it has to be 4 points, it turns out. It can't, invariants involving less than 4 points are completely trivial, all right? And we'll be 100% precise about why that is the case in the section that follows. But first, I wanted to ask a question. Is the cross ratio visible? Okay, is the cross ratio visible? I hinted, right, that if we looked at that picture of supposedly equally sized tiles, right, that perspective view of a tiled floor, that something about it was telling our brains that these are equally spaced tiles. But the question is, can you in general see, right, and see is in quotes here, can you see the cross ratio in some sense? Well, there's a nice question that you're going to do in your next homework set. Let me actually, yeah, there we go. Okay. So if we take 4 equally spaced points, so p equals 0, q equals 1, r equals 2, and s is equal to 3 on the line, then compute the cross ratio. You see that it's 4/3. Well, since cross ratio is preserved by projections, then any projective image of these points also has to have the same cross ratio, right? Any projection of these 4 points, under that projection map, the cross ratio has to be preserved, so this has to be 4/3. Okay, so the question is, do 4 points on a line look equally spaced if their cross ratio is 4/3? All right, so here's the picture. Okay, so the question is, which one of these is a projective image of equally spaced points? And you're like, I don't know. Not quite sure, maybe, right? So you might want to think about this. In fact, there's an exercise that I'm going to give you in your next homework set that's going to tell you what the correct answer is here. Okay. This answer I will leave undetermined here, but it will be talked about and it will be figured out by you in the homework. So here's the thing to notice, maybe, or maybe I should draw this picture and then I'll end class rather than start on our long list of facts that I'll talk about next time. So what is one way of looking at the cross ratio? The idea is I have 4 points on some line. So here's just some line. I don't care about what this line is, and here's just points. Okay, so here's my PQRS. Okay, here is a point. Let's see, did I draw it to, is this actually going to fit on the paper? Maybe. So here's my point we'll call big P. Okay, and I'm going to draw lines connecting P to each of these. Okay. S might be a little bit too far over. We might have to move it for our purposes. Okay. All right. So here's my 4 points on a line. Let's take a line that, say, crosses the 4 points like this, or crosses these 4 projection lines like this. So I get points that look like the following. So here's P prime, here's Q prime, here's R prime, and here's S prime. Okay. So what must be true is that this cross ratio of the 4 points P, Q, R, S must be equal to P prime, Q prime, R prime, S prime. Okay. All right. And so looking at this, the question is, length is clearly not preserved. That's out. Ratios of lengths are clearly not preserved. Again, in this particular example, you can just compare to see that that's not the case. Right, and so some of these are going to get, some of these individual lengths are going to get stretched more than others relative to others, right? So ratios of lengths aren't going to work, but the cross ratios of these points are the same. Okay, so this is the key. This is a key picture to think about. I can draw a simpler one next time that that you're more or that is more canonical and shows up in basically every text here. It's not in this text that we're using, but it's a very basic image, so I'll draw it, like I said, next time. So that's the plan. So anyway, you have your exam 1 due tonight, and someone was asking about office hours in the chat. So I'm not going to have office hours today, but I will be on email. So if you have any lingering questions about the exam, then tell me, and I will try to get back to you as soon as possible. And if I haven't answered you by the deadline, you don't have to worry and submit something unanswered. You can just you can submit what you have, and if I answer you like an hour after midnight or something, then you can submit it an hour late, and I won't dock any points off. So there's it's a semi-hard deadline of 11:59, but if you submit it a couple like an hour or two late, that's okay. Anyway, so let me know if you have any questions, and I can't promise I'll be 100% super helpful like I would be on the homework, since it's technically an exam, so I'll maybe intentionally be a little bit less directly helpful as I would be for homework, but nevertheless, that's the idea. Anyway, so let me know, and so homework due tonight, don't forget, and I will see you all on Wednesday.